Right, well, let's go ahead and get started. So officially my test review is Thursday, but really my test review is today and Thursday morning and Thursday evening, because just to make sure that I cover everything. Remind me to get the QR code before you go. And so I'm pretty familiar with this test because the 3 times I've SI'd for this class with Manal, the test has been very similar. So I have a really good idea as to the kind of stuff you need to know. So let's take a look at some of the concepts first that you have to understand in order to do these capacitor and inductor problems. So what we're looking at today are the problems where you have a switch and you have something changing at time t equals 0, and you have to draw the circuit before and after and figure out the currents and voltages at different times. So key to doing that are these concepts that we're going to talk about right here. If you don't understand these concepts, you're not going to get the right answers when you draw those circuits. So there are lots of answers to this question. I didn't know how to ask it without giving away the answer. But what is true about the voltage across a capacitor? I mean, it's a voltage, yeah. It depending on the circuit. So you're on the right track. It does change over time, but can it change? So it can change over time like this. So it can decay, and it can change over time like this. But you said like if it's connected to a battery, and then it'll have the same voltage as the battery. So let's say it's right here, and it has 9 volts. And then you throw some switch and the circuit changes. Can it be at 9 volts and then suddenly be at 3 volts? No, it can't do that. So it can't change instantaneously. And by not changing instantaneously, I don't mean this. It can have smooth change, but it can't have a jump. So now you probably know the answer I'm looking for the current through an inductor.
Same thing?
Yep, same thing. It can't change instantaneously. So for instance, let's say I had a battery and a switch and an inductor and a resistor. So right now, clearly, what's the current through the inductor in this circuit? It's 0. And so it's 0. And then when I throw the switch, it has to start at 0 and build up to some until it reaches it's actually going to be more like that. I think I'm not sure what the graph looks like. It'll reach its steady state, but it has to start at 0. And then once it's like this and it's closed, if I then open the switch, it has to start from where it is and then decay to 0. Okay. Now, can the current through a capacitor change instantaneously? And this one is yes. The current can. So even though the voltage has to be smooth, the current can change abruptly through a capacitor. Can the voltage across an inductor change instantaneously? And the answer to that is also yes. All right. Okay, so how would you find the voltage across this capacitor before t equals 0. So before t equals 0, this switch is open. And so before t equals 0, the circuit behaves like this. And here's R1, R2, and R3, and that top branch, it's like it's not there, and that's VS, and this is C, and we're looking for this V. Now, you had said it's the same as the battery. That would be true if I had this circuit. So if I had this circuit right here, if that's V and that's R, then in this case, V would equal VS, because the capacitor is going to act like an open circuit, and so if it's been in this position for a long time, it's just like it's open right here. And so everything that's on the top is all at the same voltage because there's no current. So that's all at, if this is VS and this is ground, then everything up on top is at voltage VS, and everything at the bottom is at 0. And so if I take the top, if I want to get the voltage, that would equal the top minus the bottom, that would be VS. So that would be true for this circuit, but the circuit that we have is a little more complicated because it's not just the battery, I've got these other resistors in here. And so it is true that it will act like an open circuit if it has been in this position for a long time. So I know that the current going this way, so I know IC equals 0. So how do I get that voltage?
The voltage division over R2 plus R3?
That's right. So when I look at this circuit, I'll just draw my capacitor like an open circuit. R2 and R3 are in series, so I can write them as one resistor, like that. And then often the way to get the voltage across a capacitor is to find something it's in parallel with, because things in parallel have the same voltage. And so in our simple circuit up above, since there was no current flowing, since this resistor was not acting, since there's no current flowing, then the capacitor and the voltage source were in parallel. But here I do have current. And since I have current, I have to pay attention to that. So I've got current going around the outside. And since I have that current, then I can use voltage division to find the voltage across the R2 and R3. So the voltage across the R2 and R3, which will equal the voltage across the capacitor, will be my source voltage times the voltage, the R2, the resistance R2 plus R3 over the total resistance, which is R1 plus R2 plus R3. And that's how I would find my voltage. Can anyone think of another way to find the voltage across R2 plus R3 besides using voltage division? Oh, hey. So besides using voltage division, we could do this. What is my entire resistance in this circuit?
R1, 2, 3.
Yep. So my equivalent resistance for the entire circuit is R1 plus R2 plus R3. Do I have the same current through all of my resistors? Yep, yep, they're in series. So my current is going to be Vs over R1 plus R2 plus R3. So now, if I wanted to find the voltage across R2 and R3, I know that voltage is equals current times resistance, or it equals our current, which was Vs R1 plus R2 plus R3, times our resistance, which was R2 plus R3. And if you look, that answer is the same as what we got up here. So, just different ways. There's always different ways of doing things. Okay, so now let's take a look.
So can you explain
Yeah.
how you got to where it was like open in the middle? Because at first you said there's no current, which made it open, and then now you're talking about current, so I'm just kind of confused.
There's no current through that middle branch. So it is open in the middle. There's no current going through here, but there is current going around the other parts.
Why is that?
Because they're connected, so it's a complete circuit. And so whenever you have a complete circuit, you'll have current. So if I look at these parts right here, is there a path for the current to flow, although, to make a complete
Yeah.
circuit? Yes.
I get that, but like, how did we get to where we can draw the capacitor to like be open?
Steady state.
It's because it's been in this position for a long time. So if it's sitting here, for a capacitor, if it's been sitting under DC conditions for a long time, what happens is it gets charged up, and it's as charged as it can be, and so no more current can flow through it. And so it's just sitting here with, and it literally is like this. It's got most capacitors will have like a plate here and a plate here, and there's no current can go across here. And so it's just the current comes here, and if it went down here, it wouldn't have anywhere to go, so it doesn't. It just keeps going this way.
And that's like kind of like you're talking about like infinity, almost at the time or whatever.
So this is when we say a capacitor has been here for a long time. So a capacitor, the way the current works, so I have this circuit. I've got a switch right here. So right now, there's no current anywhere because it's open. So this is not charged. Our voltage is 0 because there was no way for it to get charged because there's no way for current to flow. But what happens when I close the switch, the voltage can't change instantaneously, so it has to start at 0, and then the voltage is going to build up until it gets to have the same voltage as this voltage source. And once it does that, it can't charge anymore. And if it can't charge anymore, it can't let any current flow through it. And so this is after I close the switch, this is what happens. So after a long time, it acts like an open circuit, or I think the way your professor does it, it makes it act like a battery because it has a voltage now. So it's sitting here with a voltage on it, but no current can flow through it.
So the question is asked, like, what's the voltage across the capacitor for T equals 0?
Right. So at T equals 0 in this circuit, you would close this switch, and that would change the circuit. So all the before T equals 0, all that means with this circuit is it looks like just this bottom part, and there's no switch in the bottom part. And so before T equals 0, you would assume that it has been like this for a long time.
Yeah, that's what
Okay, so now does that make sense? Okay. Yeah, because at t equals 0, then things start to change. Would y'all like to look at what happens when we close that switch? Okay. I think we should. Okay, so when we close the switch, the circuit changes a lot. And this is, I recognize this problem now, and I know some people won't like it. Okay, this was acting as an open circuit. That may change, we'll see. So when the switch closes, I get a connection from here to here that is just a wire. And we pretend like wires have no resistance.
So would it just like take out R2 basically?
Yes, it shorts out R2. So R2 is shorted and it plays no role anymore because no current's going to go through R2. What current in its right mind would go through a resistor when it has a free path to go through? So our circuit now looks like this. And remember, our capacitor was charged up with whatever charge it had. It had some charge that we calculated. So right at t equals 0, it looks like this. Now, at t equals 0, our voltage on the capacitor still has to be this because it can't change instantaneously. That has to be its voltage. So we know what the voltage is here. And we know what the voltage is here. Now let's see, what would we do from here? We would say, okay, so let's say that my question was to find the current through the capacitor. Find IC at t equals 0. Now the current can change instantaneously. Can we find out what the current is right here? Could I find I1? In general, whenever you're looking for a current, if you have a resistor and you have the voltage on either side of that resistor, then the current is going to equal VA minus VB over R. And so the current across R1 would be VS minus VC over R1. What would I2 be? Yep, so VC minus 0 over R3. Now, I can't do that with IC because there's no resistor. So how would I find IC?
I1 minus I2.
Yep. So I would use KCL, and whatever doesn't go to I2 has to be IC. So IC has to be I1 minus I2. So that's how I would find it.
Then you can subtract 0 for I2 because you put your ground after R3.
Yeah. And I did that implicitly, even though I didn't draw it before, because when I said the voltage here was Vs, then that means that the voltage here had to be 0.
Okay.
So I had assigned ground without drawing it earlier.
So IC would be whatever, like, you said the capacitor maxes out current. So it would be whatever the capacitor, like the max they could take.
No, it's just going to be whatever I1 minus I2 is.
So it keeps building up in the capacitor, maybe?
We would find, what we would do at this point is we would find the voltage across a capacitor. So you have the formulas that you need to know for this test, or that you'll have on your formula sheet. Or do you make your own formula sheet? Okay, so I put so much stuff in my formula sheets, it's ridiculous, and I end up like using almost none of it.
Every time. Security blanket.
And then the rare times that I need something that I put on there that's like kind of obscure, I get so excited. Let's see.
I brought in my digital logic 1 binder to the digital logic 2 test.
I did that. I was taking a graduate physics class, and we were allowed to use anything that we had produced ourselves, like any notes, any homework that had to be that we had produced ourselves. And I said, "Can I bring like my homework from my undergraduate classes?" He's like, "As long as you did it yourself." I'm like, "All right." So these are the main formulas that you'll want. Let me just get the whole page. So I will talk about the different kinds of functions at another time. So I'm not going to worry about those right now. You have your capacitor formulas right here. I don't think you need this, but I would have it anyway. It's just a formula for finding the capacitance of a parallel plate capacitor. And these are your formulas for an inductor. And for the kinds of problems we're doing right now, we would use this. This is how these integral equations are how you find the voltage and the current during this transient time. So it's called transient because it's not steady state. Remind me to QR code for you as well. And so what you would do for the capacitor is you would say, in this problem, it's not steady, it's changing. So it's the voltage at the time where you start plus 1 over C times the integral from the time that you start to t of I dt. And if you wanted I is C dV dt. So in our particular circuit, where were we? We're right here. Okay. I think I know what I would do, but I want to make sure, because let me see if this particular problem, what the actual problem was, see if I have a solution so I can make sure I'm telling you right. $41. Close your eyes. Okay, yeah. All right, so it was not, for some reason, it's not on that page in the book. So this is what we actually want. Yeah. So I don't know why it's not on that page in the book. So these are the solutions. If you solve those equations as integrals, you get these, and these are the main ones that you're going to want. Here we go. That one is, it's got more in it than you need. Okay, this is the current through an inductor. And then we also want the voltage through a capacitor. And these are the problems that I was going to do later, use these. So this is where you would have to find, this is if your switch is at t equals 0. So then the voltage across the capacitor, you have to find the time constant. And the voltage across the capacitor will equal its voltage at infinity plus its voltage at 0 minus its voltage at infinity times e to the minus t over t. So in our particular circuit, our tau, this is our circuit. So tau is RC. So how would I find, what does that R refer to?
Our equivalent.
R equivalent. So what would R equivalent be on this one? So this is like we're starting, I didn't mean to be doing this problem because we're starting with the hard one. So it's which R are we talking about?
So,
Both.
But through where the capacitor was.
So what you have to do is you have to look at it from the point of view of the capacitor, and you ignore sources. So here's our capacitor, and here are our two resistors. So from the point of view of the capacitor, are these resistors in series or in parallel? Parallel. So R equivalent is R1, R3 over R1 plus R3. And so our time constant is C times R equivalent. So then our voltage at time t would equal our voltage at 0, which we calculated already, no, that's not, it's voltage at infinity. We have not calculated voltage at infinity yet, so we need to calculate voltage at infinity.
Now it just gave the voltage over the R3 resistor.
So the voltage at infinity, let's take a look at that, and this is also going to like play into the questions that you were asking about how the capacitor behaves. So now we're going all the way to infinity. So when we get all the way to infinity, the capacitor will be fully charged up with no current flowing through it. So its voltage is going to be the same as the voltage with something that it's in parallel with. And it's in parallel with this R3. And so at infinity, it will equal Vs times R3 over R1 plus R3. Just doing voltage division. And then, now we have V at infinity. You could plug that in, you could plug that in. We found tau, you could plug that in, and that would get you the equation for the voltage. To get the equation for the current, you would do C times the derivative of that equation. So, I didn't actually mean to do that problem, because that was harder than I intended, but I did it. Yay. Okay, let's take a look at this one before t equals 0. Before t equals 0, what is the current? And let's do the current as it's drawn. So I drawn going down. Before t equals 0. So how does an inductor behave if it's been sitting there for a long time? Like a wire. So what is this current going to be? Yeah, so it's actually negative 10 the way it's drawn, because it's drawn going down, but the current would really be going up. So I would equal negative 10 milliamps, because it's shorting out the resistor. It's just acting as a wire. Let's find...
Would we have to worry about the other half of the circuit? Like, I understand that the switch has sort of, like, doesn't let the power or the amps flow through the inductor, but I would wonder if is it just stuck in its own perpetual loop?
Yeah, and that's an excellent question, because so we see that we know the current is going here, current's going here. is there any possibility that some of this current is going this way? Is that at all possible? Or do we know that it all has to go this way? And the answer is we know it all has to go to the right because we know we have 20 milliamps here. We have 20 milliamps here, so we have 20 milliamps here. We have 20 milliamps here because it can't go that way. So we have 20 milliamps coming down this way. And if any of that 20 milliamps went in this direction, there wouldn't be enough for there to be 20 milliamps here, which there has to be. And
Why does there have to be 20 milliamps then?
because the current has to be the same for everything that's in series. And so all through here has to be 20 milliamps. And so since I have to have 20 milliamps here and I have 20 milliamps coming down, then the current in this direction has to be 0 milliamps. And so when the switch is in this position, there is no interaction between the two sides of the loop. And similarly, I have to have 10 milliamps here because I have to have 10 milliamps here. And so I have to have 10 milliamps going through that inductor. Okay, let's see what happens when we throw the switch. So now I have oops. Okay, now by the same reasoning we just went through, when we throw the switch, is the 10 milliamp current source going to affect what's going on in the right-hand part of the circuit once the switch gets over here? Yeah, so by the same reasoning, we know that this all has to go through here. And so we're just really not concerned about that part. So we have this. And we know at t equals 0, we know the current through this inductor has to be 10 milliamps in this direction because it can't change instantaneously. So what does the current have to be through this 40 ohm resistor at t equals 0? It has to be 30.
30?
Uh-huh. Because it's got 20 from the current source and 10 from the inductor, so it has to be 30. Now that's just at t equals 0 because the current through the inductor is going to start decaying. No, it'll start building up. It'll build up until it's 20 going down. So what would I at infinity of the inductor be? 20 milliamps in that direction. Yeah. And what would I at infinity through the resistor be? 0, because it would be shorted out.